Okay, so we are on our last section before the big exam, and we're talking about calibration methods. And I kind of like this article. Something about MRI machines or something, and I blew this part up. I think what caught my eye, I guess the nurse or somebody, other than the fact that babies shouldn't be over-radiated, was that this had been going on for some time. So, calibration, whether it's finding, the amount of analyte in a solution or using a machine, calibration is really important. You just assume it's right. So you want to make sure you do it right. Method of least squares. Okay. And we're going to avoid all the math, thank goodness, to get in this least squares, also called regression analysis. But the book likes to call it least squares, so that's what I'm going to call it. Brandy, the method of least squares finds the best blank blank through data that is theoretically supposed to be blank. You answer? You answer any of those? What's that?
Parabola.
Best parabola? No, it's not supposed to be parabolic. It's supposed to be linear. So that's the last part. But what's the first part then? Finds the best blank blank. Your data is supposed to be linear. Finds the best. Well, yeah. Yeah, all your answers are really right, but they don't fit blank blank. What line? Straight. Because isn't that what you end up doing? You end up trying to get a ruler and draw the best straight line through all these dots. Right? That's why I think of straight line, because hardly anyone plots out their own stuff anymore, right? But you could, right? And you plot it out, and you have these dots over the place. You have to draw your best straight line through there, and that's what this does. What is the equation, Daisy, of a straight line? Y equals mx plus b. It's supposed to be an mx plus b. So on our little plot here, Albert, conventionally, where's the y and where's the x? And yeah, that means x is down here. Then how about the little m and the little b, Alyssa? What are these guys? Yeah, that little m. What are these? M is the slope. The y-intercept. Right. Okay. If a least squares analysis is performed on your data, Marlena, what's the result? So you go into Excel, or whatever the case is, whatever software you're using, and you do a least squares analysis. Or it could say regression. What do you get out of that? What do you get? What's the product? It does all the calculations for you. Anybody help her?
Line of fit.
You get a line of fit. Okay, be more specific though.
The line that best represents all the data.
Yeah. That's because that's just answering the first question. You're getting the best straight line. What do you get?
The slope of it.
Yeah, you get a slope. What is the result? A slope. What else do you get?
Y-intercept.
You get a y-intercept. And then you get something else. What else do you get? If your data is really linear, this value is going to be really close to 1, if not. What is it called?
Your R value.
Yeah. What the heck does the R stand for? I remember it's either they call it R squared. I guess R stands for regression. I'm not so sure. But yeah, you get this value, the R value, for lack of a better name. I should look that up. right? Really close to 1. Good job. Or great fit, right? Very linear data. Okay. Would have been really easy for you to draw a straight line through there. There's 2 assumptions with this least squares analyses. Delta y is much, much bigger than delta x. What they're trying to say is the errors, the uncertainties associated, because all these measurements have uncertainties. So what we are really talking about, it's coming up, is calibration curves. I don't want to get ahead. Am I getting ahead? Nope. Let's see. Yeah, that's okay. All right. Well, this is where we're heading. Response or signal versus concentration. This is really the big goal for today, right? These calibration curves. And least squares analysis says that the error in for this to work, the error in the response needs to be bigger than any errors that you have associated with concentration. It works the best. And all the errors in the response or the signal are about the same. Okay. So those are some assumptions that they use in the calculations. Okay. Assume separate experiments are performed where each experiment matches one of the below theoretical equations. Pick 2 variables that are linearly related, because if these 2 variables are not linearly related, it cannot be theoretically linear, therefore you can't do regression analysis, least squares. So we pick 2 variables that are linearly related to allow least squares analysis to be performed, to plot in each equation, and predict what the theoretical slope and y-intercept will be. So you're doing an equation with y equals mx plus b. You would plot what versus what to get a linear relationship. Yeah, plot y versus x, right? Your slope would be, all right? Yeah, there's my slope. And everybody knows the y-intercept will be the little b. Okay? So if this is your equation, that's what you'd end up with. Whatever that little m, it could be, well, that's why we're getting into this stuff like this. VF equals VO plus AT. Yeah, there's actual physical meanings to all this, but what would you plot? What could you plot and you get a linear relationship? You could plot which one? There's 2 velocities. There's 2 speeds in there. Plot VF versus, you could plot it versus T. You could also, let's follow this one through first. If you plot VF versus T, right, what is your slope? Slope is going to be little a. If you can see that, you're seeing this right. Right? That's the advantage of plotting the final speed versus time, is your slope is going to be a. What would be your y-intercept? Yeah, that initial speed. V naught. What if I didn't? What if I plotted? Yeah, that's good. What if I plotted not VF versus T, but I plot VO versus VF versus VO? Let's do that one. What would be your slope? Theoretically, if your data follows that equation, theoretically, slope would be what? To me, all of the answers are right here in our y equals mx plus b equation, because that's the equation for a linear relation. We're plotting y versus x. So VF versus VO, our y is really VF. Our x is associated with down here on the bottom. X is associated with VO. So y equals mx plus b. What's in front of the x? A 1. Your slope is going to be what? 1. Your slope would be 1. What would be my y-intercept? AT. So all we're doing is we're playing around with y equals mx plus b. Here's another one. D is 1/2 gt squared. Pick something to plot on the y-axis. Pick something to plot on the x-axis so that you... D is a nice thing to put on the y-axis. So you want to put D there. Fine. I heard a T, right? Put a T on the x. Sounds like a conventional thing to do. But if you do that, what's left over? You end up with D is 1/2 g t. I'm going to rewrite it like that instead of saying t squared. Make it fit with y equals mx plus b. Wait. I know you see it, but we'll see if everyone else sees it. What is the y-intercept? If I plot D versus T, what's my y-intercept? 0. Plus 0. What is my slope? 1/2 gt. T is changing on you. You don't have a constant slope. It's going to be not a linear relationship. Can't do that one. This is before we had T down there, so you can't do that one. What could we do? Okay, G. But G, now I have to tell you what G is. G is gravity. G you can't change. So you can't plot versus G. Plot it versus t squared. Okay, you plot it versus t squared. Write down what you think the slope and y-intercept are. You're plotting it versus t squared. You see what the slope is? 1/2 g. What's my y-intercept? 0.
So the reason you couldn't do it with T is because
No, because you plot it versus t, your slope, theoretically, now remember your data is following that equation. Your slope is 1/2 gt. But isn't t, aren't you plotting t, changing t all the time? Your slope isn't going to be constant. That is not a linear relation. So you can't make that equation. You can't make that plot. Another one, F equals ma. Pick 2. Tell me what the slope and y-intercept are. Go ahead, yeah, and then figure out what the slope and y-intercept are. If you get it, here's your big finale right here on the end. Destiny, what did you plot? What versus what? She put F up here. Let's do a different color here. She put, we already did a lot of purple. Let's do green. You did F up there, and you put, she put A down there. A is the X. So, did anybody else do that? Okay, I hear a lot of people did that one. Okay, so what would be the slope then? Right? Slope has to be the mass, right? The y-intercept would be 0. All right, the big test. What would you plot to get a linear relationship here? Oh, I think I should pick the variables. Well, this may, yeah, anything. You figure it out. What could you plot And theoretically, there is a linear relationship between those. That allows you to do linear regression, all of it. But if you don't have it's not theoretically supposed to be linear, you can't do least squares. So you got to be careful in what you plot. Now, to give you some hints here, to make big M, little d, and little c, they're changing. Kind of like when you see like F equals MA. See how M can change, A can change? They're not, what I mean is they're not like a G. They're not like a constant. So all those guys can change. M, D, and C, they can all change on you. Right? None of them are universal constants like gravity. Kevin, you got a guess? What could you plot? Okay. It fits really nice, right, if you do that, because then you have y equals mx plus b. Okay. That sounds good. I like that one. Let's let them off there. Sochi? What about your x-axis? What's that? I can't hear her. What did you say? M squared? Does that look like it'll work? All right? Your slope then would be 6, y-intercept, this mess 48d over c. All right? So I guess it depends how things are behaving. So that would work. All right. So calibration curves, that was just getting you into it there. Why are linear calibration curves preferred? So first let's make a calibration curve here. We have maybe, they call it signal or response. And then you have concentration. Right? So you make a whole bunch of concentrations and hopefully you get this nice linear data. Why? Why would that be preferred, Victoria, over, I don't know, erase a couple of these, make them a little more loopy? Right? It could be kind of odd down at really low concentrations. Why is it preferred to have linear?
Would it be easier to find what you're looking for?
Yeah, you're right. It's easy because remember that what's really going on here is you're going to literally have an unknown, measure its signal, and go across and down, right? And if it's not linear, shoot, look at all the data points you got to get. So that's why you like linear, and then if you pick the right variables, that helps too. So how is an external standard calibration curve prepared, and how is it used to determine unknowns? Okay, so before we get into this, we should probably get into some idea of standards. This is a horrendous compound. It's horrible. It kills people, right? This blue stuff. Okay, so I made up this big concentration of the blue stuff, right? This would be called a what solution? Stock or concentrated, right? Stock or concentrated solution. Okay, and then someone actually dropped some in the, I don't know, a swimming pool or something, right? Take a scoop of it. This would be the, how would you describe this? This would be the unknown, example of an unknown. Someone took the exact same crazy bad blue stuff and dumped it out there in Elmendorf. Took a sample of Elmendorf. This would be called unknown. Okay, so there's really two different kinds of unknowns to worry about. Okay. Stock solution. So when you make an external, how is an external standard calibration curve prepared? Well, get a bunch of flasks, right? They're all 100 mils, so that's kind of nice. Take my concentrated stuff, right? And I know the volume. I could do MIVI equals MFVF and make a bunch of these, okay? But I probably want to put this guy on. I need a signal or response. So I'll probably use the UV Vis because it's blue. So I could use an instrument like the UV Vis or a little Spec 20 or something, right? And get its absorbance signal. Pick the wavelength and see how strong its absorbance signal is. And then I can do MIVI equals MFVF to make a standard. Maybe put it in the machine to make sure that, you know, he's either above or below it. Because I want, see what I want to do? I want to make these, I want a data point one below and at least one above. So I can, you know, go across like that. So I'm kind of, when I'm making these standards, I kind of be careful like that to make sure I have at least a really dilute one and a really concentrated one. So make them all, plot them out, right? So you'd have your concentration and your signal, right? And you plot all that stuff out. Okay, just make sure you have a standard that's below and above. And they like to call, technically, people always call them standards, but technically they're called external standards. Okay. So we make the calibration curve. How is it used to determine the concentration of the unknown? So you could literally get a ruler, right? Draw the best straight fit, but we're not supposed to do that. We're supposed to do a what analysis? Starts with an L. Least squares. Do a least squares analysis, right? Get the slope, get the y-intercept, right? So we'll get this, and then we'll do least squares, and then we'll get our slope and our y-intercept. So it would look something like, whoop, it would look something like my signal equals m times the concentration plus my little b, right? Y equals mx plus b. So I know what my little m and my little b are. Got them from their least squares. And my unknown, right? I'm just going to measure its signal in a little Spec 20, get that number, and then solve for concentration. You can do the whole ruler thing, right? But people won't be very happy with you. And if you're really, really careful, you can get good results. But right, just so much easier. Use regression. That's what it's there for. Okay, so that's how we make the external standard calibration curve, and that's how we use it to determine the concentration of unknowns. What if the response signal of an unknown is above or below that of the standards? Right? I only have 3 standards. Here they are. And my signal, oh man, it's way the heck, I don't know, it's way the heck down here. That's my signal. But man, I can only go from, right, here's my concentration range. Right, those are my 3 dots. I want to go right there. Can I use the regression equation and solve it? Right? I can plug in my signal. I can put in the m and the b and solve for concentration. You can mathematically do it, but are you supposed to? Right? You're not supposed to, because you don't know what's going on down here. This guy could be really curvy. It may not be linear down there. So you can only use calibration curves within the range that they're calibrated. You can't go outside the calibration curve. Maybe that's what was going on with these little babies. They were way outside their calibration range. We don't know. Or maybe they just did things wrong. Okay. If the solution... Okay, well, what then? What would you do? You have to make a standard that's even lower. You have to. You have to make a standard that has an even lower signal. You don't have any choice. I hope it's linear. Okay. So now, instead of this nice, clean swimming pool water being my, the solution, it's the Elmendorf. So, can I make a little cuvette of him and put them in the machine? And all right, don't you see the problem there? Something here, and there's a lot of crud in here. Odds are, with all the algae and all this stuff in there, yeah, fine, filter it and everything. But odds are there's organic stuff in there that absorbs blue. Yeah, I mean there's stuff in there all over the place. So you can't use an external standard calibration curve. Okay. The answer really is right here. You have to use standard addition technique. We'll say what it is, but a sample is to be analyzed. What is meant by the matrix of the sample? Very different matrix. What's the matrix?
The interaction between the analyte and the other things in the solution.
Yeah. What's the name of the, Eric said it. What's the name of the, what word do you use to describe what you're after, what you're looking for? The dangerous blue stuff. The A word. The analyte. We're after the analyte. So the interaction of the analyte with everything around it, I just like to say the matrix is everything but the analyte. It's the chemical environment of the analyte, right? That's what the matrix is. It's the chemical environment. It has everything to do with what Eric said, right? How the analyte interacts with the environment and all those sorts of things. So it can be really complicated with Elmendorf. And notice how in our external standard calibration curve, we just put in a little bit of the stock, and then we diluted it up with water. Our matrix was identical. And we didn't even really think about it, but our matrix is identical. It's identical with the unknown and with all the standards. They're all identical matrices. Matrices. So how does the standard addition technique work? So when your matrix, you want that matrix to be the same as what's in your unknown. And when that matrix is not the same, you have to do standard addition technique. Okay? When that matrix is not, you can't make it. Or why would you even bother to analyze this and to figure out what its matrix is? Why? You don't care. You're just after the blue stuff. So what you do is you end up having the sample, this ugly mess of solution, be your matrix. You use it. Because what we're going to do is, here we're going to get 1, 2, in this picture we have 4 flasks, right? And see if you can make sense of all this. C standard probably stands for what? Concentration of the standard. So that would be this stuff, 11.7 molar blue. Okay, that's the concentration of the standard. The C unk probably be the concentration of that hazardous blue stuff in the unknown. Okay, so that's my Elmendorf. That's my Elmendorf. That's my Elmendorf water. That ugly, messy stuff. Right? It's really gross, and all that stuff is in there. Okay. So with these 4 flasks, what do? V-unk. V-unk. What does that probably stand for? Volume of the unknown. So you take some of this out, V-unk, and put it in every single flask. And it's the exact same volume. I don't care. 20 mils, 30 mils, whatever. Right? Put in the exact same volume of unknown in every single one. And then, you see what they did? VSTD, probably volume of the standard, right? So they took different volumes of that standard, right? And just spiking is really the word. They didn't spike flask number 1, though. All right? They didn't flask him. But flask 2, 3, and 4, they spiked even more and more and more. Okay, so our signal for our blue should be going up. From flask 1 to flask 4, it'll be going up. Okay? So you plot it out. they plot the volume of the standard they added in each flask versus the signal. Yeah, and here we have one that's a 0 though, right? Because we didn't spike it at all. And then we spiked it 3 other times. And hopefully it's linear, otherwise all this isn't going to work. Okay. And then we just jump down to our little standard addition equation. Concentration of this hazardous blue stuff in our unknown, which is in the Elmendorf, you just solve for it. Little b and little m are what? Slope and y-intercept. And how do you get those numbers? Least squares analysis, or regression, whichever word you like to use. So you're going to have to perform that analysis on it. So you get your little b, little m, plug them in. We already said CSTD, concentration of the standard. The volume of the unknown that you put in each flask, right? Just put all those numbers in, and we'll solve for the concentration in our unknown solution. That's called the standard addition technique. So pretty much all you're doing is you're using the unknown as the matrix. Okay. Internal standard. Gases are really difficult to sample reproducibly. The internal standard of the addition of internal standard reduces dramatically sampling fluctuation errors. If you the instrument I'm talking about is really the gas chromatograph upstairs. Probably one of the most fun, the easiest to use, and the most powerful instruments that I can think of to date right now, because you put it in that machine, it separates everything out, it gives you the best guess that it thinks of that's in there, and it's really nice. But it's a gas. What's the problem there? Let's say you're going to sample a gas. The red is the analytes. Okay, so you sample it one time. That's about how much you get. You sample it another time. You sample it a third time. All right? It's hard. Nothing changed. It's just a gas. Gases are really hard. It's called sampling fluctuations. It's really hard to get the same amount every time. And if you're trying to make a calibration curve, trying to do an analysis, see if this guy, is he above the alcohol limit or whatever, it's going to be really hard. So how do they get around this? The word is internal standard. So let's say that, let's say it is a blood analysis. Ethanol is our analyte. So what we're going to do is, in our unknown, we're going to introduce another compound. Oh, it's something that's really kind of similar to ethanol, probably like methanol. You want it to behave, so that one's your analyte. All right, and this one is my internal standard. You introduce it into the guy's blood sample, or whatever the heck you're analyzing, whatever solution you're analyzing. Introduce this internal standard, right? Get it really nice and well mixed up, and then you inject it into whatever machine you're using in sampling a gas. So not only does it get your analyte ethanol, but it gets some internal standard in there. Again, it gets some internal standard, but less in injection number 2. Injection number 1, I got a lot, I guess. So it got more internal standard. Injection number 2 didn't get much, so it got less internal standard. And number 3 got a whole lot for some reason. That means it got a whole lot more internal standard. So what didn't change? Calibration curves are all about plotting. They're all about plotting right, concentration. And what's on this axis, the y-axis? Response or signal. They're all about that. So what signal is there? I mean, it looks to me like they're all changing. Right? The signal of the ethanol, the signal of the internal standard, they're all changing. But what isn't changing? The ratio. Exactly, Matt. The signal of the, it doesn't really matter which is which. Usually it's, people like numbers bigger than 1. So I'd say like the ethanol signal divided by the internal standard signal. Yeah, so you just plot it versus the ratio. And then your sampling fluctuations go out. Okay? The ratio stays the same, even if you sample more. You sample more ethanol, well, then you also sampled more internal standard. The fluctuations go away. Okay. Suppose you carry out an analytical procedure to generate a calibration curve like that shown in 411. Then you analyze an unknown to find an absorbance that gives a negative concentration of the analyte. An absorbance that gives a negative concentration of the analyte. What does that mean? That's kind of a hard thing for you to answer without taking a class like instrumental analysis. No one's had instrumental in here, right? No one's had instrumental in here, so I can't pick on anybody. If you, pretty much, you almost have to do this to prove it to yourself. You've used the little spec 20s though, right? Those little spec 20s where you get absorbance values. Do you remember using those? Well, if you don't, what you got to do is you got to put in a little cuvette with water in it. Then you push, you know, the 0 button or something, right? And it goes, and then it reads 0. And then you put in your sample, and then you write down the absorbance. Okay? What if your sample was really, really dilute? And when you put in your cuvette with the blank with the water in it, you put it in the wrong way. You know, because sometimes they have that clear side and that frosty side. You put it in the wrong way. So now it's shining through that frosted side. Not much light is getting through. And then you put the 0 button. Then you put in your sample. More light is getting through than what the background had. That's negative absorbance. So it's I don't know how you'd answer a question like that. I wouldn't really worry about it too much. I just thought it was interesting. Okay. Using the calibration curve in figure 4-11. Find the quantity of unknown protein that gives a measured absorbance of 0.264 when the blank is 0.095. So what are they doing here? Here's our amount of protein on the x-axis. Our corrected absorbance is on the y-axis. Corrected probably means what? Corrected. There's a hint in the question. They gave us 2 absorbance values, right? Here's our sample, and there's a blank. Its corrected absorbance would be, what would you do to the blank with the blank? Subtract it out. Subtract out the blank. So for this unknown protein, its corrected absorbance would be 0.264 minus 0.095. And you need to know it, otherwise how else can you calculate its concentration? So pretty much y equals mx plus b. What's my y with that plot? The corrected absorbance. It looks easier if you write it this way. And my x, everybody, is amount of protein. Okay. So we know what the corrected absorbance is. We just told you how to get it. All right, subtract those 2. We're after the amount of protein. Well, we're just missing what? We're after solving for this one. Well, we need to know what? Mathematically, we know that number. We need to know the slope. We need to know y-intercept. It's got to be in there. Right? You see it? It's got to be in that question.
Oh, they have the equation like that.
Oh, so it's like y minus y1 is equal to 0.095?
The corrected absorbance is 0.264 minus 0.095. But what did you say, Matt? I'm just looking up here. No, they did a regression analysis. You just got to read the small print. You could always do change in y minus change in x, but you're going to have to read what those numbers are. Oh, ugly, right? Okay. So you can figure out the slope and y-intercept are there. And that's about it. And there's a few other questions, but I think you got the gist of this. So be spiritful tomorrow.